Okay, so we're going to be talking about the definite integral like we talked about in class. We, instead of now using the expression the area under the curve f of x between x equals a and x equals b, like we talked about in class, we're going to use this, what we call the definite integral. Okay, and as I showed you in class, that's what the definite integral looks like. So just to remind you, that symbol right there, this notation means the area under the curve between the curve and the x-axis on the interval from a to b, and just like we see here. So this here's f of x, and I do want to point one other thing out, that when you're finding the area between a and b, what you're going to be really doing here is you're going to be adding up an infinite number of rectangle areas. And I want you to start thinking about the definite integral as adding up an infinite number of things. So the integral from from a to b of f of x dx adds up an infinite number of things. Okay. Now, when you just think of these things as rectangle areas, then that's fine for certain integral problems, but then if you can think of it as adding up an infinite number of things, then we can apply the integral concept to actually finding the length of an arc. We can find the volume of a three-dimensional object, and those are the two big things that we're going to be using integrals for, is finding arc length and also volume. In addition, I should say, to finding the area between a curve and the x-axis, or finding the area of a region. Okay, so keep that in mind. When we integrate, we add up an infinite number of things. Okay, and these things in this case, the integral from a to b, all you need is the area of one rectangle. Should use a different color. So we're going to be integrating from a to b, adding up an infinite number of areas of rectangles in this case. Okay, so all you need to do, in other words, to be able to put these integral expressions together is write the integral symbol, write the lower limit of integration. I want to make sure that these things are clear. This is like, well, not like, it's the lower limit of integration. And this would be the upper. I'll just write upper limit, and that means the upper limit of integration. And this right here represents the area of one rectangle, whereas the width of the rectangle is the dx, and the height of the rectangle is the f of x. So all you need really is to find one rectangle. And I'll continue to, we'll continue to look at that in section 5.4 as well. But right now, keeping those things in mind, I wanted us to talk about some properties of, or rules of integration symbols, and the limits of integration, and what do we do when there's all kinds of different ways that we can write the area of a region, but I wanted to make sure we're clear on a couple other things. When we want the area under the curve, okay, if a is less than b, then area under the curve we integrate from left to right. Okay, in that case dx is a positive number. So if f of x is above the x-axis, then the integral from a to b of f of x dx will be a positive number. Okay, well, you probably hadn't thought that it could be anything different than that, but now I'm going to throw you a curveball. Whereas, if b is less than a, and we're determining the area of the curve from right to left, okay, in that case d of x dx is negative, and if f of x is above the x-axis, then when you integrate from a to b, no, that's wrong. That's wrong. There's a typo right there. You're actually integrating from b to a, so caught that typo right there. So the integral from b to a, if f of x is in fact above the x-axis, then the area will be a positive number, but when you integrate from b to a, you're going to get a negative number. Okay. It's going to start making a lot more sense when we start doing examples. So let's just take a look at some more properties of integrals and see what goes on here. I want you to take a look over here at down in the very bottom box. I think this chart in general, if you want to take a look at that, that's great. I'm not necessarily wanting you to memorize a bunch of rules. What I want you to know is really the concept here, and that's what we're going to focus on. Okay. So if you integrate from a to a, in other words, when the lower limit and the upper limit of integration are the exact same, then you're not moving left and right. You're not adding up any rectangles at all, and therefore there is no area. So I want you to think of this definite integral as area. Okay, and then if you integrate from a to b, you're going to get the exact same thing as if you flip-flop the limits of integration and integrate from b to a, you're going to get the same exact number, but as a negative number, or you're going to get the opposite of the integral from b to a. And sometimes this is helpful when you're solving some integral problems, is flipping the limits of integration. So you'll see the practical application of this later. But from a to b gives area, b to a gives the negative of this area. So it's still area, but b to a gives you the negative. Okay. Now the last one that is going to come into play today is when you integrate from a to b, you're finding the area from a to b under the curve, and you add to that the area from b to c. So it's just like the transitive property of real numbers. You also get that with integrals, and so the integral from a to b plus the integral from b to c, when these numbers match, these guys right here, when the upper limit of one matches the lower limit of the other, then it's just the integral from a to c. Okay, so the total area from a to b plus the area from b to c is the total area from a to c. So that's kind of a lot of talking here, and I'm going to go ahead and just stop this video so we can just do some problems in the next video.